Every force has a magnitude and a direction. That means we have to think about two things at once. So hang on to your hats while we explain and explore how to use vectors. Mass is a scalar property. It's only a number. It can't be negative, for example. Here I am driving my car. If I look at the speedo, it tells me I'm doing 20 miles per hour. The only thing that tells me though is my speed. There's no direction. You don't know which way I'm going. So speed is a scalar quantity. It only has magnitude. Other examples of scalar quantities which don't have a direction associated with them are energy, time, and volume. If I want to know something about direction, then I need a vector quantity. If I tell you I'm going to walk 20 paces north, then I'm giving you a vector. I'm telling you that the magnitude is 20 paces and the direction is north. If you give someone directions, you need to give them vector quantities. Vector properties have magnitude and direction. Other examples of vector quantities are electric current, acceleration, and of course, force. Thinking of forces as vectors helps us describe their effects on objects and the resulting acceleration. The length of the arrow tells us the size or magnitude of the force. The direction of the arrow tells us which way the force is acting. Here is an example of a spacecraft in deep space, far away from the gravitational pull of planets or stars. This is an object falling, experiencing the force due to gravity, which we call weight. It's actually very hard to find examples where there's only one force acting. In the two examples that I've just given, the spacecraft had to be away from any gravitational fields, and that's pretty tough to do in the universe. And the object that was falling experienced no drag or air resistance. Here is an example of a pond skater sat stationary on a still pond. The two forces acting on it are in opposite directions. You can see how the direction of a force is important. In this case, both arrows are the same length, and so the weight of the pond skater pulling it down is equal in size to the surface tension from the water pushing it up. The two forces cancel out and the pond skater can sit there quite happily. We call the overall force acting on something the resultant force. In the case of the pond skater, the resultant force was zero. Everything cancels out. If there's no resultant force acting on an object, then it can't speed up, slow down, or change direction. And Newton pointed this out to us. So what if the resultant force wasn't zero? To explain this, I'm going to talk about a skydiver. During this example, I'm going to consider the forces acting vertically and ignore any sideways forces. When our skydiver first jumps out of a plane, they experience gravity pulling them down. We call this their weight. The resultant force is therefore down and the skydiver accelerates. As they get faster, the air resistance or drag increases. This causes the resultant force to decrease. Eventually the magnitude of the weight will equal the magnitude of the drag, but they will be in opposite directions. The resultant force will now be zero and they will not get faster. There's two things to note here. Firstly, the weight never changes, and secondly, the maximum speed we call the terminal velocity. This is quite fast though, and typically for a human being falling normally is about 120 miles per hour, and it would be very uncomfortable to hit the ground at that speed.
Ouch.
So the skydiver opens a parachute. Now the parachute opens, there's a big increase in drag, and it becomes larger in magnitude than the weight. The resultant force is therefore upwards, and so that is the direction of the acceleration. When an acceleration acts in the opposite direction to the motion, we often call it a deceleration. The skydiver now slows down, and as their speed decreases, the drag decreases. Eventually, once again, the size of the drag is equal to the size of the weight, and the force is balanced. If the resultant force is zero, the skydiver will not speed up or slow down anymore. They're now falling at a much slower and safer terminal velocity. Let's now look at how to handle situations where there's two or more forces acting in different directions. To find the resultant, we need to add the individual forces together. Take this box with three forces acting on it. We call this a free body diagram. It is used so that we can visualize the forces acting, but it is not that good at helping us find the resultant force. Instead, we draw a vector diagram. Drawing a vector diagram can take quite a bit of practice. First, choose a force to start with and draw that force vector. To add our next force, we need to start it where the last one finishes. We often use the expression tip to tail to describe how we add the vectors. Once we have added all our vectors tip to tail, it's time to draw the resultant. Remember, the resultant is the total of all the forces. We start drawing the resultant at the beginning and finish it at the end. One way of finding the resultant force is to accurately draw a scale vector diagram, and you do that obviously with a pencil, a ruler and a protractor, so don't forget to take those into an exam if you've got an exam coming up. Also, don't forget to add on a scale. You can now use the ruler to measure the magnitude of the resultant force and the protractor to measure the direction. Sometimes it may well be easy to use Pythagoras' theorem to calculate the magnitude of the resultant force. There's more resources on the website and there's links to that in the description. If you found this useful, please do support the channel by liking, subscribing and commenting, and for now you could watch this.